everybody, and welcome back or welcome to the channel. Apologies for the lack of uploads. I've been on holiday, then been unwell, just been too busy. But anyways, I'm back today starting a brand new series on didn't leave myself enough room there, but binomial expansion and the binomial theorem. Today we'll be starting with just basic binomial expansion, which is a fundamental skill needed for both AS and A2 because these can get really quite complicated. So you may be wondering what binomial actually means, and you may have come across this term before. Might sound similar to something called a polynomial, which you'll recognize from quadratics and cubics, etc., etc. But anyway, the term binomial means two term. Obviously, bi means two, nomial means term. But altogether, binomial expansion is expanding a bracket which contains two terms inside. You can have all sorts when it comes to this. AS, you'll have ones like these. And then when you get to A2, you can have ones that involve fractions and surds that may look like this, which obviously look a little bit more scary than these two, but these are the sort of ones that I'll be covering today. All we're going to be doing is laying the groundwork. There is a formula, just a prerequisite there, that you can use to, I wouldn't say cheat, but there is a formula that you can use to do these quickly. But I will show you the way that we do it without using a formula to a certain extent, but it just helps you to understand what is going on, okay? If you'd like to skip to that video, I'll be publishing one next week. So if you can hang on for a little bit and just practice this, I'm sure you'll be absolutely fine. Anyways, I just want to take a first quick look at this term here, x plus 2 all squared. As you can see, there's two terms inside the bracket, an x and a 2. And for argument's sake, we'll call the x a and the 2 b. You've probably seen this before when you've been just expanding brackets as normal in maths at GCSE. Some of you may use FOIL. Personally, I don't like FOIL. I prefer to use a box methods where you put the terms either side of the box and expand it and collect the like terms. But there is one other way, almost a cheat way, that I was taught at AS that makes expanding things squared a little bit quicker. And in word terms, it's to square the first term, double the product of the two terms, and square the last term. Algebraically, it looks a little something like this. So we've got squared the first term, double the product of the two terms, and then square the last term. And you may be wondering why I've put these two ones here, and I'll get to that very soon. But I'll just work it through for you so you know that this is absolutely correct. Have a go at working it through yourself, whatever way you'd prefer. And if you did work it through, hopefully you got x squared plus 4x plus 4. Now, binomial expansion is this in a nutshell. Okay? The sort of questions that you'll get will often be to expand things like this up to a particular term. So it could say expand this up till x cubed. Now obviously you can do it by just multiplying them out individually. So 2x plus 3 times 2x plus 3, then times that by another 2x plus 3. But that'll just take forever. And more often than not, ones that are as simple as that are often worth only 2 or 3 marks. But we can use something that was invented in 1653, or more specifically the 11th century. The Chinese did discover it before the French mathematician Mr. Pascal, and that is something called Pascal's triangle. This might be a familiar thing to some of you if you're a little bit of a maths geek, but I would highly encourage you to go and watch a video on it. It is one of the most interesting things mathematics has ever created, and I'll show you why. I'll draw it very quickly, only up to 4 rows, but I can talk you through some of the cool little features of it. Okay? And there we have it, up to the 4th row. Now, we start at the top, number 1. First number sort of makes sense. But we call this row 0. Our first row, well, second row, row 1, row 2, row 3, row 4, etc., etc. And this triangle goes on forever. It's infinite. Never stops. And how it works is taking the 2 numbers above and adding them together to get the number below. If you ever, as a child, had those puzzle books, some of them had the numbers at the bottom and you had to fill up the triangle. This is essentially how it works, but the other way around. And as you can see, if you took your 3 and your 3, they add together to give you your 6, your 3 and your 1 to give you the 4. The one thing about Pascal's triangle as well is that the 1s are always going down the side. That never changes because there's nothing to the other side. It's just 1 plus 0, basically. But there are a couple of cool features, and I'll just talk you through it quickly, going off on a bit of a tangent here. The diagonals, they all have something very special. The first one is a 1. The second diagonal are the counting numbers, so 1, 2, 3, 4, 5, 6, 7, etc., etc., etc. Our third diagonal are what we call triangle numbers. Then we've got tetrahedral numbers and etc., 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 that sort of thing. As we go down, I think is the coolest one. We have the powers of 11. So, sounds a bit confusing. But anyway, 11 to the power of 0 is 1. 11 to the power of 1 is 11. 11 squared, 121. 11 cubed, 1,331. 11 to the 4, 14,641. And this is true for the whole triangle, which I think is absolutely amazing. But anyway, you may be wondering why Pascal's triangle in general. Just why? You know, it's a big triangle that doesn't seem at first to have anything to do with binomial expansion. But if you look a little bit closer, more specifically at our row number 2, and take a look at our first little example here with our squared, we have the same numbers. And this is how we know what coefficients, so the number that goes alongside another number, we have in our expansion. Simple as that. So let me just write that down for you. And there we have it. We use this triangle to find the coefficients in any expansion that come from the nth row. So we'll say that our power is n, and when we do a binomial expansion, we need to go to that row. So in our case, the squared, we need to go down to the second row here, and that'll show you the coefficients that need to go in front of our binomial. But now you may be wondering, what's going on with these here? Our A's are B's and why they're squares, whatever. And this also follows a very neat little pattern. And that is... I'm just trying to give you something. I'm just trying to give you something spooky to forget. I'm just trying to give you something. very special pattern is that the powers of a start at a to the n and decrease to a to the 0, and that our powers of b start at b to the 0 and increase to b to the n. As you can see here, we're starting at our power of n, which is 2, then we go a to the 1, and then we go a to the 0, which is just 1, so we don't tend to include it. And for our b, we start at b to the 0, go to our b to the 1, and then go to b to the n, which is squared. That might overwhelm you a little bit. Okay, I've just shown you this very strange triangle, these two very strange rules, and you're probably feeling a little bit overwhelmed. And so the easiest way to show you how this works is to just go straight into an example. All right, and we shall do that now. So our first example is to expand x plus 5 to the 4. Like I said at the start of the video, you could do this very long-windedly by constantly multiplying x plus 5 over and over again, 4 times to be specific. But these questions, something like this, will only be worth 2 marks. But there are still quite a number of steps involved. More often than not, they'll also have a part 2. But anyway, let's jump into our first step. And that is to identify our a, our b, and our n. And this will allow us to use our 2 rules and Pascal's triangle to expand this example. Now I tend to write them either next to it or underneath. It shows the examiner that you understand what's going on. I tend to write it like this. So our a is x, our b is 5, and our n is 4. A is always the first term and b is always the second term. Now it doesn't matter if the x was here and the 5 was there, that is still a, that is still b, and that is still n. Okay, now we've done that, we can have a look at our triangle, which I shall just pass back in by here. And our value of n, as we can see, is 4. So we need to go to the 4th row in our table, which is 1, 4, 6, 4, and 1. Now these will be the coefficients that will go with our expansion. The easiest way for me to do this is to write it vertically. It'll make more sense as I go through, okay? Trust in the process, we will get there. Like I said, I tend to write it vertically and this will make more sense. So our values of the coefficients always come from our value of n that comes from Pascal's triangle. In your exam, you won't have access to Pascal's triangle. No one will expect you to learn Pascal's triangle, especially if you've got terms that will require you to expand up to x to the 7s or 8s, etc., etc. So I'm just going to show you a quick way on my calculator on how to do it. Now I've got the old Casio FX991EX. If you've still got this, please keep hold of it. It's a fantastic calculator. Don't like the new ones as much, but anyway, you can still press the same buttons. It'll still work. So go into your menu settings, go to table, which is number 9 on this calculator. And what you want to do is type in your value of n, which is 4. Then we need to go to our NCR button, which is shift and divide on here. NCR, don't worry about what it means, just learn this, and then put an X on the end. So you should end up with something, if the light is right, 4CX. You can ignore G of X, and we want to start at 0, just like the triangle does, and end at row 4. And here we've got our 1, our 4, our 6, our 4, and our 1. And this will work for any value that you need to. All right, so that's just a very quick way of working it out on your calculator without writing out Pascal's triangle and memorizing it. Okay, all right. Anyway, our next step will be to Write out our powers, and this comes from our second rule, that our powers of a start at a to the n and decrease to a to the 0, and then our powers of b start at b to the 0 and increase to b to the n. Let me write it out and you'll understand. Now I've missed out b to the 0 and b to the 1. I'll still write them alongside. I'll put them in brackets though. And the same for the a's as well, because as we know, anything to the power of 0 is just 1, so we can just ignore it. And anything to the power of 1 is just the same number. Okay, and you'll get something that looks a little bit like this. Now often I don't really write anything here, so you can almost just block those out in your mind. And it sort of makes sense once you wrap your head around what's going on. You've got your a's that start at a to the n, our n is 4, and decrease all the way down to a to the 0. And you've got our b's that start at b to the 0 and increase all the way up to b to the 4. And it's as simple as writing them out in this specific order, no matter what value of n you're using. Whether it be n to the 7 and you've got 8 values to write out, you'll start at a to the 7, go to a to the 0, and you'll start at b to the 0 and go at b to the 7. Simple as that. And all you have to do now is just fill in the blanks. And there we are, filled them in. As you can see, we substituted our x's where the a's are and substituted our b's, 5's where the b's are, sorry. And for our final step, all we do is multiply through. Now the most important thing to remember on these is what your powers are. So don't forget that once you've multiplied everything else together, your x will still have the squared or the cubed or to the 4. They won't disappear. And then you multiply everything by the coefficient at the start as well. So for example, if we take this row, we've got 6, lots of x squared, lots of 5 squared. So this is 6 times x squared times 25. And you work it through, slap plus signs in between, and you're all good to go. So in the end, it'll end up looking like this. And that is our expansion completed. As you can see, it's a lot quicker than just multiplying this over and over and over again. You can see our a's decreasing here. You can also see our b's increasing in this number value here. That'll change depending if that's a negative number, also how many values of x you've got. But this is really as simple as it gets. Always remember to include your squares, your cubes, and whatever power you need on your x's. The way to check is to look if that is decreasing. Gets a bit more complicated again when there's fractions involved, but for this, just double check that it is decreasing. Okay? Right, I'm going to do another final, slightly more complicated example, but it still works just the same. So, it looks like a little bit of a jump here, but this one will probably be worth 3 or 4 marks. However, it is the exact same as the first example. So, for our first step, we identify our a's, our b's, and our n's. Don't fall into the trap of forgetting your coefficients in front of your x's and your minus signs. That is a big mistake we see a lot, so just be extra careful with that. All right, and then we move on to our second step. and that is to write in our coefficients. Now, you don't always have to do the a plus b to the n, write them all out, and then fill in. You can just go straight to the fill in stage, but I'd advise when you're practicing questions to start off with, you write them out. So we'll find our values for n equals 5, just the same way that we did it with before. 5, NCR x, ignore g of x. Our range this time is from 0 to 5 with our step of 1, and we'll get that our coefficients will be 1, 5, 10, 10, 5, and 1. So, for our second step, we need to write in our increasing and decreasing a and b powers, just like this. There we have it, that's our a's and b's written out. The best way to check if you've done it right is that there's a gap at the top right and at the bottom left where our a and b to the 0 both go, and that our numbers decrease from 5, 4, 3, 2, 1 and increase down here from 5, 4, 3, 2, 1. So now we get into our filling in or our substitution, and it's always worth putting in the brackets even when you know that the expansion and the substitution are going to be fairly simple. This is to make sure that you don't get confused with your minus numbers when you're squaring them. When you try and working out big numbers like this on the calculator, I always advise put brackets around everything. This is because if you just do -3 to the power of 5, it's going to do it BIDMAS way. It's going to ignore that minus, going to do 3 to the 5 and then put the minus on at the end. That is incorrect. You just need to include brackets at every possible stage to avoid complications, okay? And that how we fix that is by writing in the brackets in our workings. So let me do that quickly. And there we have it all written out nice and neatly. You can see exactly what's going on here. And even I've put the 2x in brackets here, just to be neat, mathematically correct, and to make sure that there's not going to be any mistakes. I'd advise how you do this is by just typing it into your calculator and then adding in the x to the power at the end. So, for example, I do something like this, which is 5 bracket 2 bracket power of 4 bracket minus 3 bracket, and this will give you your first answer, and then at the end you can just put x to the 4. Okay, so work that through quickly and we'll come up with our final answer. And there we have it, our final expansion here. Apologies, I made a mistake. If any of you are still watching, please don't judge. We all make mistakes in maths, and as long as we recognise them before we get to the end and we move on, jobs are good. Okay? As you can see here, we've got change in negatives and positives because of this -3 and the powers it's been raised to, so always watch out for those. And our values of x are decreasing down here. Alright, and this will conclude our first video on the binomial theorem, just the basic binomial expansion. I highly encourage you to go away and have a practice yourself. There are ways of checking if this is correct by setting a value for x in your calculator, typing this in first and then typing this in afterwards. If your answer is the same, then you've obviously done it correctly. But just try and be accurate with your maths, especially when it comes to the multiplying bits here. As long as you follow all the simple steps, you'll be absolutely fine. All right, I'm going to wrap this video up here now. Thank you very much for watching. Congratulations if you made it to the end, because I know this is a long one. But anyways, we shall continue with this in our next video.